Johan told me that we're supposed to conclude by 22. So, whatever time will allow us, I have material for 5 days. So, Oh, by the way, if you want 5 days of T-SQL materials, so just a bit of self-promotion if you don't mind. We have this advanced T-SQL class that we run regularly, and in Sweden, there's one class I'm delivering this week, but then the next occurrence is planned on November 24th till the 28th. So Johan will share the script files with all of the demonstrations. You have this information if you're interested in the next kind of round in this header, right? All right, good. So I wasted 1 minute of your time already, I'm sorry. Let's proceed to looking at a solution that will give us, remember, a plan that instead of doing a full scan of the index, what in our scenario, remember, cost us 3,000 reads. So instead of the 6 that gave us 3 million reads, we went along with the scan, giving us about 30,000 reads, and those are sequential reads, right? Unlike the 3 million random ones. So clearly the best choice for the low density case, but now we are looking for a better option for the high density case. And I gave a very extreme example. Maybe we have 10 distinct partitions. Let's say with cheapers, it's more typical the case where you have a small number of distinct cheaper IDs that each handles over the years many orders. I will use the same customer scenario, but imagine we had a very small number of distinct customers, and now with only, let's say, 10 of those, doing a raw number-based solution will give us the very same scan. Here the optimizer doesn't figure, hey, it's better for me to go and do this with 6. It still uses the very same plan, and we still pay 30,000. But now it's 30,000 sequential, not compared to 3 million random reads. Here the potential, if we have a series of 6, 30, that's all, 30 random reads with only 10 6, So now the question is how we get this solution, and as mentioned before we left for the break, the apply operator will allow us to do it. So let's see how. So what we will do is we will go and look first at a single query that for a given customer gives us a seek into the first matching row for that customer and then scans 3 rows. So, well, a top operator, someone suggested here earlier, will certainly give us this kind of plan. So let's go and change the use of the row number with a top operator. So we'll say top 3 where the customer is equal to a specific one. So let's say that we are testing it now with customer 1. And of course, adding the ordering specification, we'll say order by, order date descending, followed by order ID as a tiebreaker. Now let's go ahead and look at the query plan. So naturally, the best query plan is one that does a seek in the non-clustered index, as you can see, the POC index. And look at the seek predicate. It's based on only, well, it's a bit low there. You can see it's based only on customer ID. So here, the seek goes to the first row for that customer section in the index. That's already 3 reads, and now it scans 3 rows. It might seem a bit misleading. The predicate says customer equals 1. And what if the customer has 1 million rows? How do we know that it touches only 3 and not more? This has to do with the bit confusing thing about how we read execution plans. Most people analyze the query execution plans depending on the data flow order, which is like the order of the arrows from right to left. But the internal API call order is not the data flow order. Actually, the plan starts executing from the root node. And this node invokes an API against the node to the right that says, give me a row. And then this node invokes an API against the node to the right of it that says, give me a row. So that's the internal execution order. And the top operator, you will see it has this property called top expression, which here happens to be 3. And therefore, 3 times it invokes the API that says, give me a row. So once we reach that first row for the customer 1, we return 1 row, second row, third row. We are not asked to proceed, and return another row. That's how you can see beyond the performance measures. If you look at I/O measures and so on, you will see it's only 3 reads, that's all, right? So just to understand why it might seem a bit confusing for people, but we're not really fulfilling the complete scan of all rows that satisfy the condition, only the number that the top requests. So this does give us the perfect plan for a single case, but as mentioned already, we don't have this kind of partition by, available within the top specification. But what we can do, we can go and use a cross-apply operator against the customers table and have this query embedded as the applied table expression query against each of our customers. So let's do this. So we will go here and say, select from our customers table, and then let's call it C in short, and then we do a cross-apply, and then here will come a correlated table expression, right? So let's go and name it A for apply, and now what gets correlated is this, of course. Instead of referring to the constant one, we'll refer to CCust ID from the customer row, yeah? So we don't need to return the customer ID from the order. Of course, it's available to us in the customer row, but all the rest certainly is. So let's go name the inner table O, and then say O.custID equals C.custID, and then we can go and collect elements from both sides. So the part that is similar to a join is that if I get 3 rows for customer 1, they are matched with the row for customer 1 from the left side. And if I get 3 rows for customer 2, again, they are matched with the row for customer 2 from the left side. So I'm now allowed to return information from both sides. Yes, so maybe the company name I will obtain from C, and then from A, naturally, we will want to return everything. Here's an example where the star is not a bad practice. Well, unless you place this in a view with schema binding, it will prevent you from using stars. But anyway, here we were explicit about the list of elements, or the set, I should say, of elements that we want from this side. So no surprises there. And now let's have a look at the query plan, and you will see, without changing anything about the data, this time I got exactly the plan that I was aiming at. It would have been nice if the optimizer knew to do it itself. I mean, this is one of those things that you expect the optimizer to do, yeah? Investigate the data density information and then choose the appropriate, strategy. Sometimes the optimizer does this, sometimes it doesn't have logic to do this. For example, when you use a row number function, it doesn't have any other kind of a strategy to optimize it other than a full scan. So you need to know in what areas the optimizer is flexible and in what areas it isn't, and you need to know when to intervene. So here we see it scanning some index from the customers table, collecting the customer IDs and the company names, and in our kind of illustration we had 10 distinct cases, and then for each case you see a nested loops that then goes and does exactly the same work that we saw previously for this constant customer 1. Only this time, notice the SIG predicate, it doesn't say customer ID equals 1, it says it's equal to the C.custID, right? So now this gets executed exactly as many times as the number of customers, and in the example where we had 10 customers, this would be 30 reads. Now, you see how 2 different solutions get very different performance, even though they have the same logical meaning. One of them is stable in terms of the I/O cost. That's the row number function. Never mind if you have dense, non-dense partitions, 30,000 reads is what you pay. This solution changes quite dramatically in its cost depending on the density. And you certainly don't want to use it when you have very low density. So just remember this, it's not something you always want to use. You need to recognize the scenario as a high density scenario and the POC index that is available, right? And that's when it gives you the kind of optimal performance, right? So this was the kind of POC example. By the way, it will make usually a lot of sense for us to take this logic from the inner query and encapsulate it in an inline table function just to simplify the query logic and make it easier to maintain. So we will create an inline table function. Oh, let's do sales get top orders. Let's make sure we don't have one. And then create the function, and then pass a customer ID as input, and we could make also the number of rows that we want to filter an input parameter, and then we'll say returns table, and then as return, and now this part, the query that we just copied from the derived table, and of course you replace those values, the number with the input number, and the customer ID will now be the input customer ID. So now we have a nice inline function that implements the logic, and then in our original query, we can just go ahead and specify the function passing cCustID as first input and the number 3 as second input, and because it's an inline function, it gets unnested much like any other table expression. So when you look at the query plan, it's no different than the plan that we just got when it was embedded directly, but there's no question about the form that we have now being a simpler and easier form to maintain, right? Now, before we proceed to the next kind of scenario, most of you probably know this, but just for the sake of completeness, I will say that if the customer gets 0 rows back from the right side, the customer row is not returned. And in this sense, it's a bit similar to an inner join. Like in an inner join, if we don't have a match, we don't return the row. Yeah. So we have a couple of customers in the table that don't have any orders, and therefore we don't see them. So you see we got 263 rows in total. So we have an outer version of apply that will return those 2, right? So if we run it now, you will see 2 extra rows exactly for those 2 extra customers, and somewhere in the result you will see the rows with nulls coming back from the right side, much like an outer version of a join, right? All right, so moving on to our next scenario. So we have a kind of classic unpivot sort of tasks, and the simple form of unpivot we can handle quite easily with an unpivot operator. But there are more complicated unpivoting tasks where you don't want to unpivot only one set of columns, what the unpivot operator does very easily. You want to unpivot multiple sets. Let's see an example. So I have here a table called sales that has such an example. So what we have here, if we look at it over here, is the following. Select from sales. So you can see we have, we have a set of columns representing quantities in different years. We have another set of columns representing values in different years. You try to deal with this with the unpivot operator, it doesn't know how to cope with this. It only knows how to cope with a single set of columns that need to be rotated, right? How do we deal with this? Well, we have an answer now for all of my questions using the apply operator naturally. How do we do this? Well, think about it. If we go and do a cross apply, now here we have access to the elements from the left row, and we evaluate this apply table expression per left row. So nothing prevents us from taking the elements from the left row and construct from each row 3 rows, again by using, remember, the values clause to define this kind of derived table. Just define 3 rows. 1 for 2012, 1 for 2013, 1 for 2014, that's all. You know, I mean, after you think about it and you get the hang of it, it's quite straightforward. So we'll create a table called A, and from each source row, what do we want to see in each split target row? Well, one column will hold the year, so let's name it order year. Another column will hold the quantity for that year. Another column will hold the value for that year. Unlike what a normal unpivot does, it creates usually only 2 columns. One for the names, one for the values, basically. Here we have one for the names, that's the years, and then one for each measure that we are producing by doing this kind of a multi-column kind of unpivoting, right? So let's call one column quantity, the other column value. That's what they mean for us. And now let's construct those. So values, now 3 rows. 1, 2, 3. What will we have in each row? Well, the year we define with a simple constant. Yeah, so for example, if I'm now building the 2012 year, what will I put in the column or the year? Well, the constant 2012. In the second row, I'll put the constant 2013. In the third row, I'll put the constant 2014, okay? Then, for 2012, naturally, the quantity part comes from the column quantity 2012, and the value part comes from the column value 2012. And as you already see, in a very similar manner, for 2013, or let's wrap the text so it will be easier to follow here, we'll have just 13, and for the third year, we will have, similarly, quantity 2014 and value 2014. So easy. Now, we don't need to show the original columns. Yeah? So we will, of course, return only what we need to see. So customer ID, that's from the left side. Let's call it S. So S dot customer ID. And from the applied table expression, naturally, you certainly will want to return everything. Beautiful technique, as you can see. Once you get kind of convenient with the apply concept and the values clause, those things become very natural to write. Also, from a performance perspective, highly efficient. You will see a constant scan operator that constructs basically a table from a set of constants, which the values clause generates for us. Very, very efficient. You will compare it to quite a few other solutions that people use for this. Not only they tend to be more complex, they do much more work. They do it with much more effort. And if we have multiple CPUs and most systems nowadays, unless you have some virtual machine that restricts you to one CPU, Apply tends to use very efficiently parallelism. And in fact, there are some queries that don't get very good treatment of parallelism, and the way to improve this is by splitting the work to sort of partitions that appear in another table, and you do this apply, and you get much more even distribution of the work, you know, to the different CPUs. Yeah. So here is a tiny little table. You don't see this, but with a big enough table, you will get very, very nice parallel planes, right? So this is yet another scenario, more complex unpivoting. And then a more recent kind of solution that combines the use of apply and a feature that was introduced in SQL Server 2012 to deal with a very classic kind of need to compute percentiles, and more specifically, the most classic one, the median, or the 50th percentile. Yeah? So first, let's start with a very small table, and then we'll do some performance comparisons with alternative solutions. So we have a very basic table, T1. And you can see there's some kind of a group column and some kind of a measure. And we want to compute a kind of classic median. There are two kind of statistical models to compute percentiles in general. One called discrete distribution model and the other called continuous. For the median, the 50th percentile, what does it mean? The discrete model says the median is supposed to be the middle point, right? But the discrete model says it has to be one of the values from the set. It cannot be an invented value that is somehow interpolated. So if we have an odd number of elements, it's easy. The median is simply the middle point in all models. But the problem is more when there's no such exact point. Like when we have 4 rows, the discrete model still says it has to be one of the existing values. So the discrete model says you return the closest one to the missing. You know, in the median case, it's smack in the middle, the missing value, so they go for the first, basically. So in this case, the discrete model will return 60, but then the more commonly used one is one that implements the continuous model. The continuous model says, let's imagine that the distribution continues evenly, and therefore we can interpolate the missing value from the existing ones by using a formula. In the median case, it's just an average, because right in the middle, if we assume continuous distribution, is the average of the two middle points. If it was a different percentile, like let's say the 30th percentile, you would take the two values that surround the missing one, and you will need to compute the one that appears at the 30% point between the two, basically, right? That's what it means. Anyway, such a classic need, you know, many applications that deal with statistical analysis need to compute medians. How do we do this? Well, let's start with the fact that SQL Server 2012 introduces functions that already do this. These functions are implemented as windowing functions, even though in standard SQL, it's not supposed to be like this. In standard SQL, you are supposed to say group by the group column, and then for each group, you're supposed to return. Now you would use not a windowed function, but rather a normal group function, what's called an ordered set function. Meaning it's a group function, but it has ordering relevance. So you are supposed to say a percentile, and now if you want the discrete model, you say disk. If you want the continuous model, you will say cont, and then here you will indicate the percentile. For median, this would be the 0.5, yeah, 50%. And then this clause is defined in standard SQL for ordered set functions called within. I just invented a new clause. So within group, and then here we say order by, and now the value column is the part that defines the order. And in this case, it's supposed to be our median, right? Let's wrap the text a bit. All right. Now this isn't implemented yet in SQL Server, the concept of ordered set functions. So Microsoft said, you know what? As a first implementation, it's easier for us to implement it as a windowed function because we already have the infrastructure for windowing. So what you will do, instead of defining group by GRP, you will go and define it as a partitioning element. So instead of group by, you will say a partition by. All right, oh, sorry. I placed it in the wrong clause. So you will add an over clause, basically. And here you will say, instead of the group by, partition by GRP. And this is something that the infrastructure already enables without them going and doing a full implementation of the ordered set functions as group functions. Thing is, with window functions, we return the aggregates or the result of the calculation along with the detail. And in many cases, it's a great thing for us. But here, we don't need the detail. So look at the result. The result returns the median calculation correctly, but along with the detail rows. It doesn't collapse like a group function does. You know, it doesn't collapse the data for one row per group. How do we collapse it? What's a small addition that will return it only once per distinct case? Well, distinct, all right? So we will just add a distinct clause, and now, of course, we get it only one per row. It's all nice and well. There's some trickiness with the awkward distinct that we need to use, but then again, it's so much easier than any other solution. You know, if you try it, people use dozens of different solutions out there. This is so much easier. Where's the problem? The plan. Look at the plan. You know, it's a good thing that I have very small font size, but you will see this very elaborate plan, and twice in the plan there are activities that take the data, write to a spool that's a walk table, do one pass to get the detail, another pass to get an aggregate. This happens twice in the plan. So if I go and run it against a bigger table, so here in this database I have same data but 10 million rows, or same structure I should say, but different data, 10 million rows, and now you run it. Now this will run for a while. Of course, we don't wait for it to complete. I will start writing a different solution that will give it to us much faster. Now there are some solutions that use a combination of row number and count and so on. They are nice, but they don't get near a solution that uses the apply operator and the offset fetch filter that was added in SQL Server 2012, what will give us a much faster solution. So here's the way it works. And this guy is still running. That's over half a minute already. Let's start writing it in a separate window. And again, first I will show it against the small set, then we'll run it against the large set. So what we are going to do, you know that in SQL Server 2012, they added this nice feature that allows us to use a filter similar to top, but in addition, we can indicate how many rows we want to skip before we say how many we want to filter. So very handy for paging purposes, you know, where we need to return one chunk of rows at a time. So instead of using the top, we say, like the usual, order by whatever, let's say order date and order ID. And then here, we use this new clause called offset fetch. We first indicate how many rows we want to skip. So let's say we have a page size of 25, we want to skip 25 and then filter 25. Or we want to skip 50 and we want to filter 25. And then we say offset 50 rows and then fetch next 25 rows only. And you realize the concept is very similar to top, but we add this skipping capability that says how many to skip before we say how many we want to filter. In terms of optimization, optimized with the same top operator, but it's slightly enhanced. It has a first portion that says how many rows to read but not pass to the next operator. And then, in addition, the top expression, how many rows to read but to pass to the next operator. So, in this example, in total, it will read 75, but return only the last 25, to the next operator to the left. That's basically the idea. Now, how do we use it along with the apply operator? Well, here's what we do. First of all, from an indexing perspective, you want to create an index. The optimal index here would be an index on MPID and quantity on our table. MPID and then quantity. And if I try to run it here, it gives you an error because I created those ahead, so the comparison between the solutions will be fair. Yeah? We already have this index in place, both on the small and the larger table. Now, our solution will go and do first a simple group by and count. Let's first count how many rows per group. So select from T1, group by, and then our group column, and then for each group, simply return the count. Right, so looking at the query plan, notice we get already an ordered scan of the index, so that's one scan, right? So if we have X pages, now we're paying X page reads to compute the count. So far, one pass. Next, we are going to compute based on the counts the parameters for the offset and the fetch clauses. So we will tell it how many rows to skip, then how many rows to filter. How do we know how many rows to skip? Well, we take the count, we subtract 1, and then we divide by 2. What's interesting is that the system, when it sees that the operands are integers, uses integer division. So we don't need to go and do rounding and those kinds of things. It already produces the correct result. Think about it. If I have 11 rows, 11 minus 1, 10 divided by 2, 5, that's exactly how many rows I need to skip. That's the offset value. If I have 12 rows, 12 minus 1, 11, divided by 2 with integer division, exactly 5 rows that we need to skip. Works correctly. Good. So now we have the right skipping number. Then how many rows do we need to filter depends on whether the count is odd or even. So we will take the count, do modulo 2, and now, if the count is odd, we need to fetch 1 value. If the count is even, we need to fetch 2 values. In other words, the result is 2 minus this kind of modulo result. So this is our fetch value. Good. This didn't add almost any kind of effort. You see the 2 compute scalars show up with 0 cost. Now, we have all the information that we need for an offset fetch, and how do we make this logic work per employee? Well, we use apply, right? So let's do it, and with this, basically, we conclude. So we'll go define a table expression that gives us the counts and the parameters. Now we do select from C, then cross-apply. Now comes the table expression that we apply. And then here we filter only the interesting values. So select from our table T1, where the T1 GRP is naturally equal to the C GRP, so we filter, that's the correlation, remember? Then comes the order. What defines the order? Order by the T1 dot value, naturally, and now come the offset fetch filters. So offset. How many rows? Well, we defined it in C, offset value rows, right? Then how many rows to fetch? Next, again, C dot fetch value rows only. And then for the filtered rows, what do we return? Well, only the values, right? So let's go ahead and see. From C, we return the group. From A, we return the value. We got, for the odd groups, only the middle point. For the even groups, 2 middle points. Look at the plan, what's added per group, not per row, per group. We get the apply doing this activity that does a seek to the beginning of the group in the index and scans how many rows? About half, right? So in total, roughly, we're scanning 1.5 times. That's it. And the one remaining thing is, okay, now let's go group by the GRP column and then apply the average to the values. And that's our median. Now, one small thing, since our values are integers, it will do an integer average, and we either explicitly convert to a numeric or implicitly by multiplying it by a numeric value. And we have our median. Now, let's see how long it took that other solution to complete. It was 1 minute and 16 seconds. That's the scary plan. Now let's try the apply plan. So let's switch to the TestDB database, run it. It's done. 1 second. The fastest solution that I had before this one took 11 seconds. That's before the introduction of this offset fetch. But the combined, offset fetch with apply is an order of magnitude faster, right? And you will look at the plan. This time you see nice parallel treatment because we have enough data to justify it, right? So in short, I told you there are so many things that you can do with the apply. And in our case, I just gave you a handful, as just a few examples. A very strong feature. I do recommend exploring it. And you will very likely find yourself, the more you play with it, finding yourself all kinds of solutions. Nice if you share it with, the community, like some of these solutions. Otherwise, would love to see you, in the November class, if you want 5 days of this kind of material. And again, thanks very much for having me. Always a pleasure to be here. All right, thank you.